measure of the number of neighbors for a node. And then eigenvector centrality is a measure of the degree of the vertex as well as the degree of its neighbors. Right? So the centrality basically captures, quantifies the topological importance of a node in a graph. So what I mean by topology, the structure of the graph, how the nodes are connected to each other. So if you look at this graph, and if you want to find out the most important vertex in this graph, if you go by degree centrality, you may think X and Z are the two most important vertices because they have a degree of 3. Again, degree means the number of neighbors. So X has 3 neighbors, Z has 3 neighbors, and so on. And Y actually has only 2 neighbors. So relatively, you may think X and Z are better than Y, or more important than Y. But that's with respect to degree centrality. Now, with respect to what is called the betweenness. So betweenness means how does a vertex facilitate communication between the other vertices. So this Y plays like a connecting point. For any of these 3 vertices to communicate with any of these 3 vertices, they have to go through Y. So if you capture the importance of a vertex on the basis of this betweenness, how much they are important for facilitating the communication. And when we talk about communication, we really want it on the shortest path. Okay, so we don't want to go on a roundabout path or a longer path and so on. So betweenness captures that aspect, like how much, what's the importance of a vertex with respect to its presence in the shortest path between any 2 vertices. So in that case, Y is actually more important than X and Z. So it depends on what aspect you're considering. Okay, so just the number of neighbors and their neighbors, or this shortest path based communication. Or there's another thing that's also shortest path based called closeness, which means how close is the vertex to the other vertices. Okay. Again, in that sense, Y may be even closer because Y is closer to X and Z is just one edge from Y to X or Y to Z, and 2 edge from Y to Z to this vertex, or Y Z this vertex, or Y X this vertex, Y X this vertex. Whereas X has shortest path of length, what, 1, 2, 3 to reach some vertices. So it's the length of the shortest path. So if a vertex is closer to every other vertex, then it may be more important. Okay, so on this basis, so you have different things that you can use to rank the vertices. Okay, so we're going to see a set of centrality metrics. We can broadly classify them as degree based. As I said, degree is number of neighbors. So, or you can say neighborhood based. So degree centrality is a measure of the number of neighbors, and eigenvector centrality, which is what we saw last time, the principal eigenvector and all those things. So we'll see them again. It's a measure of the degree of the vertex as well as the degree of its neighbors. Okay. We're going to go through each in detail later. So the shortest path based metrics, as I said, betweenness centrality, then closeness centrality, as well as something called farness centrality, which is like a variation of closeness centrality. Okay, I'm just introducing the names as we go through the detail. We'll see each of them more. Okay. All right. So now, in terms of names, we say we have degree and shortest path. Now there's a hybrid version of those two. So which means it combines the ideas from degree or neighbor based as well as the shortest path based. That's why it's called hybrid. Okay. And there's one metric based on that. It's called local clustering coefficient based degree centrality. So let us see each of them in detail. Okay, so degree centrality is the number of neighbors. So if you want to do it more mathematically, okay, we can use based on the adjacency matrix. So adjacency matrix is nothing but zeros and ones. You have a 1 if there's an edge between 2 vertices, and 0 if there's no edge. Like 0 is connected to 1, 2, and So for 0, you have 1 with 1, then 2 and 3. Then for the other vertices, you have 0 because there's no edge from 0 to anybody else. For 1, you have an edge to 0 and 2. So 1, you have 1 here and 1 here. For other vertices, you don't have an edge. So it's a symmetric matrix, you all know by now. Now, to get the degree of each vertex, you could multiply the adjacency matrix by a column vector of all ones. So we say this is a column vector because it's just one column and you have entries for all the vertices. So it's all ones. So you all know how to do matrix multiplication, right? So this is what, a 7 by 7 matrix, or no, 8 by 8 matrix, where 8 is what, the number of vertices in this graph, 0 through 7. And this is a column vector, 8 rows, 1 column. So the product of these two is also going to be a column vector, which is 8 by 1. So to get the entries, you are going to multiply each row with this column. So it's a term by term multiplication. 0 times 1 plus 1 times 1 plus 1 times 1 plus 0 times 0 and so on. So you add up all the ones that you get, the multiplication, you get 3. Similarly, it's this row, second row, multiplied by this column vector, you'll get 2. So that's the degree. Okay? So it's nothing but the number of ones in each row. So in the first row you have 3 ones, that's the degree of 3. But you want to get more formally, you multiply it by a column vector. Because I'm using this because we'll see the same approach to compute eigenvector centrality. Yes?
Do we have a reason why we multiply by all ones?
That's what, to count the number of ones. So these ones get counted if you multiply by all ones, because if it's a 0 times 1, it's a 0.
I know, why we doing all ones?
Because we want the entries for, we want the degree for each vertex, right? So this is an 8 by 8 matrix. Adjacency matrix is square matrix, right? So I want to count the number of ones. So I want a scalar value. So I multiply this, it's like a vector by itself, this row vector by a column vector. Is that clear now? This row vector multiplied by a column vector.
Is there a specific reason why we do all ones?
That's what I'm saying. The specific reason is I want to count the number of ones. So this is, the other entries are zeros, right? So 1 times 1 is 1, plus 1 times 1 is 1, plus 1 times 1 is 1. Okay? So you multiply by any other value, you won't be able to get the number of ones. If you multiply, say, by all zeros or any other number, you won't be able to count the number of ones.
So if you were looking for 3s, you put 3s over there? If you were looking for 3s?
3s? What?
The number of 3s. If there were 3s in the...
Number of 3s here, so... And you get the degree at the end if you count add the number of ones. So her question was, if you had 3s, you want to count what? Number of 3s? Then you would divide by, you would multiply this by 1/3. So there are three 3s, or in that case, if there are 4 4s, you wouldn't need such a situation. You have to find the right value to do that. If you have 4 4s, you could multiply by 1/4. You want to add up the ones actually. So I could rephrase this, not the number of ones, add up the ones. So if you want to find out the number of ones, which is because since it is a 1, adding up all the 1 is same as the number of 1s. But if there's some other number like 3 or 4, if you want to count the number of 3s, this may not be the approach. Maybe something else. Okay. Alright, so is that clear? So just get the adjacency matrix and multiply by column vector of all 1s. Okay. So now these are the degrees of the vertices. Now the degree value is the number of neighbors, so it's an integer. Now remember, in the degree centrality matrix, you want to quantify the importance of a vertex. So throughout the module, we will try to rank which vertex is more important than the others. Okay, rank the vertices. So if you try to rank the vertices based on the degree centrality metric, okay. So if you decide that larger the number of neighbors, the better, the more higher rank the vertex is. Now you see here there are only two different values of degree centrality, either 2 or 3. So in that case, if you pick 3 as the larger degree centrality and better, so 0, 2, 3 and 5. So these are the 4 vertices that have a degree centrality of 3, right? So there's a lot of ties, which means you say 4 vertices are equally important. Not really though, because you could see some vertices, as I mentioned, are structurally more important with respect to other measures, like betweenness and so on. So those things are not captured to degree centrality. Just count the number of neighbors, and since it's going to be an integer value, there's going to be a lot of ties. Okay, so that's the weakness of degree centrality. It's more easy to compute. We say it's computationally light because you just do this multiplication and it takes rate of v square time. So why it takes rate of v square time? This is a v by v matrix. So the v square entries in this adjacency matrix, and you are multiplying, say, a row with v entries and the column with v entries. So this is v multiplications, one multiplication with each term. So v multiplications to get this particular entry. So how many vertices? V vertices. So v times v is v square. So you do v square multiplications to get the degree centrality. Later we'll see like betweenness centrality will take v cube or more time. So which means you are more computationally heavy. So degree centrality is more computationally light. It takes less time. But the problem is you cannot get unique values as much as possible for the vertices, so that they can be ranked without ties as much as possible. Okay, so you have 4 vertices, the same degree centrality, which is not that good, so that you cannot rank them uniquely. So we'll see a more advanced method based on the degree approach called eigenvector centrality. So eigenvector centrality of a vertex by definition is a measure of the degree of the vertex as well as the degrees of its neighbors. So in the last module, we found what? The principal eigenvector, right? So what's the principal eigenvector?
Largest. The largest.
Is the eigenvector corresponding to the largest eigenvalue, right? So for a, like this graph has 8 vertices, you're going to get 8 eigenvalues and 8 eigenvectors. So the eigenvalue which is the largest is called the principal eigenvalue, and the corresponding eigenvector is called the principal eigenvector. And the entries in the principal eigenvector are the eigenvector centralities of the vertices. Okay, so if you run this graph through that program that I gave you for module 2, you're going to get values very close to these. Okay, for the 8 vertices, the principal eigenvector. So those are the eigenvector centralities. So now in this module, we are going to see a more mathematical approach of computing the eigenvector centralities. So you can use one of the two. So in exam, if I say use what is called this Bauer iteration method, that is the name of this method to compute the eigenvector centralities, then use this method you're going to see now. If I say use the spectral analysis program I gave you, then use that code and try to run it and get this eigenvector centrality. Or you can cross-check, if you have, for exam purposes, you can run both and check if the values are almost the same. Okay, so if you look at this, we'll go to the calculations, but let me just motivate the importance of eigenvector centrality. So these numbers quantify the